All right, everyone, welcome back. We're going to be talking about those chart integrals again, the chart problem from the AP test. And let's look at more Top Gun, shall we? On our second sortie with Maverick, speed was charted at the following values in the table below. I'm sure you can read that. In his first hour of flight, Maverick's speed was an increasing function. Okay, so I don't know. Not quite sure how that's going to play into the function, but the speed is always getting bigger. Okay, use a left Riemann sum with 4 subintervals to estimate the distance Maverick flew in the first hour of the sortie. Is this estimate an overestimate or an underestimate of the distance? And give a reason for your answer. Okay. B, use your answer in part A to estimate Maverick's average velocity during his first hour of flight. We talked a little bit about that last time, but we never actually found an average velocity. And C, use the data in the table to evaluate the integral from 0 to 1 of s prime of t. Using correct units, interpret the meaning of s prime of t, integral of. So yeah, a few different things here. Let's start with letter A. That's probably the one that's most similar to what we did. So we're going to find a Riemann sum using a left method. I think we talked about that sufficiently last time. So let's just start with by putting up our chart. Make sure you double check to make sure that you haven't left off anything. So I got a 0.2 in the middle, and right here and here. I got 0.4 here and here, 0.7 here and here, so it doesn't look like I missed anything. Next is going to be a row for delta t. Just like last time, those delta t's are not consistent with every interval, so we can't use any shortcut rule to do this. Next thing for us is to find the height of the rectangle. I'm going to reread this again, and I'm seeing that this is a left Riemann sum. So this time I'm going to find the height, which is s. I'm going to find s at the left side of the interval. Okay, let's make sure we did this right. On the left side of the interval from 0 to 0.2 is 0. And the speed at 0 is 0. The left side of the interval from 0.2 to 0.4, that's 0.2, and the speed at 0.2 is 120. So just kind of reading through all that, you can see we've got all of those correctly on the left side. And if we did this correctly, the far right value of s will not get used. And you will notice that the far right value of s, right over here, is 468. No, we're not using that. All right, now that we've done that, we're going to write our integral, and we are going to write the sum with all the products written out. Let's do that right now. As you can see, we went ahead and we wrote out all the products without doing all the multiplication. Next, we're going to write out a line with all the multiplication. And there we have it, 237. That's going to be an estimate for the distance that Maverick flew in that first, what are we looking at, hour of flight? Yes, that first hour of flight, 237 miles. The next part is this an overestimate or an underestimate? And there's no real elegant way of doing that. So what I'm going to say is here on the right side of the page, this is an increasing function, like we know Maverick's flight's velocity is an increasing function. And we're supposed to be doing a left Riemann sum. So to simulate that, we're just going to draw left rectangles into this function. So what do the left rectangles look like? You don't need to draw nearly as many as I did to realize that an increasing function combined with a left rectangular method is going to produce an under approximation. When you write this down, you just need to say as such. And it's an underestimate since the left rectangular method underestimates an increasing function. Letter B, find the average velocity, or no, the average speed in the first hour of flight. And remember what I keep saying, I think I've said it with every video we've done. The average of anything in calculus is an integral expression. Let's write out that integral expression. So here's that integral expression. The next thing for you to do is just substitute your answer from part A, which gave you an estimate for the integral of 0 to 1 of st. Luckily for us, there isn't actually any division to do. We're dividing by 1. So 237 is our average speed. We just need to write some kind of a sentence that is going to explain this. So Maverick's average speed in the first hour of flight is 237 miles per hour. Which brings us to the very last problem here. Use the data to evaluate the integral of s prime. And guess what? This is a fundamental theorem question. What happens when you integrate s prime? The antiderivative of s prime is s, so you just get a change in s. Doesn't that look like the fundamental theorem of calculus to you? The integral of the integral of a derivative is the function evaluated at ab minus the function at a. Let's try that again. The integral of a derivative is the function evaluated at b minus the function evaluated at a. Where do we get these values of s1 and s0? Maybe right here. Isn't s1 468? Isn't s0 0? So this is equal to 468 minus 0. So what does it mean? Well, if you subtract Maverick's distance at 1 minus his distance at 0, what you're getting is a change in distance, or how far did he fly during that first hour of flight. So in that first hour of flight, Maverick flew 468 miles away. Remember that his flight was an increasing function, or his velocity was an increasing function, so he never turned around and came back to base. He was always moving away from the base. So that takes care of all of the review stuff. Let's go ahead and get to the important ideas. Actually, I'm looking at this, and this is kind of wrong. Isn't s speed? So what this really should say is Maverick's speed increases by 468 miles per hour. Wow, I almost had to redo this whole video again. Wouldn't that have been embarrassing? Okay, back to those important ideas we were talking about. So you're going to use the chart to evaluate RT for Riemann sums or rectangular approximations. We talked a lot about that in the last video, so we're not going to do that so much here. The average is going to be the same average, but in this case, you're finding the average of a rate. Okay, so the average of a rate. And then finally, if you integrate a derivative, you just get a change in whatever that parent function was. Context is the change in r, or a displacement in r. Okay, go ahead and pause it here if you need to copy that down. And I'm going to move to the next problem. All right. A test plane flies in a straight line with positive velocity v in miles per hour at time t minutes, where v is a differentiable function of t. Selected values of velocity vt and the 0.40 to 40 minute time interval are shown in the table. Use a midpoint Riemann sum, show the computation, and use correct units. Explain the meaning of that in terms of the flight. And lastly, based on the values in the table, what's the smallest number of instances at which the acceleration could equal 0. So that's a new kind of problem. I'll take a look at that in a second. First of all, let's do the easy one. Let's do our Riemann approximation. This time we're doing a midpoint Riemann approximation. So let's see, if I'm doing a midpoint Riemann approximation, that means I'm going to have to skip one of these boxes because this has got to be the midpoint. So if you'll just kind of follow over here in our first interval, it's going to be from 0 to 10. And then our midpoint is then going to be 5. Our second interval is going to be from 10 to 20. And in this case, we're going to have the midpoint as 15. I think you see where I'm going with this, so I'm just going to go ahead and write out that table now. So here we go, 10 to 20, 20 to 30, 30 to 40. Let's just make sure. I remember reading that we needed 4 subintervals. So let's count 1, 2, 3. Yeah, I see 4 subintervals. Next, of course, is delta t. I'm looking at that chart over there, and I'm seeing that every delta t is 10. So that's going to give me an opportunity to factor out 10, although there's no real reason to do it. There are only going to be 4 terms in your sum. So there's no real reason to factor out a 10. In fact, no, I'm not going to factor out the 10. Don't change things. Okay, next we have to figure out where do we evaluate v. And we're going to evaluate v at the middle. So what's the velocity in the middle of the interval from 0 to 10? Well, that's the velocity at 5. I'm looking up, and that is at 9.2. 15 is 7.0. 25 is 2.4. And 35 is 4.3. Now that I've got pretty much everything set up here, I'm going to write down that integral expression with my sum. 229 miles. Now for our interpretation, I notice that the test plane flies in a straight line with positive velocity. So it's always going in the same direction, which means that when I interpret this, I can just say that the plane flew 229 miles during the 40 minutes of its flight. And there we have it. Part B here says that based on the values in the table, and I'm going to blow up this table, what's the smallest number of times that our plane, what happened here? Better. What's the smallest number of times that our acceleration is going to be 0? And since the acceleration is the derivative of velocity, I know you all know that, but it's important to think about that. Since the acceleration is the derivative of velocity, acceleration will be 0 when velocity either reaches a relative minimum or a relative maximum. Because at those points, the tangent line to the curve of velocity will be about 0. So let's see what's happening in each interval. Are we getting increase or decrease? Well, from 0 to 5, we have an increase. And I'll signify that with a plus sign over there between 0 and 5. Okay, from t equals 5 to t equals 10, the velocity increases again by about 0.3. And then from 10 to 15, the velocity decreases. Okay, so right over there, that tells me that somewhere here, there should be a relative maximum in velocity. So the acceleration has to be 0 someplace. Another way to another way to say it is that since we're looking at the tangent line's positive, then the tangent line's positive, then the tangent line's negative, somewhere in this interval, there should be a place where the tangent line is going to be 0. Let's go ahead and make these positive and negative marks throughout this entire thing. So something really interesting happened here. We had a place where the change in velocity was actually 0. So let's count how many places do we see a change in velocity. Well, here's one place between here and here. And then here's a place where the velocity has to be 0. But notice that I'm not going to highlight this entire section because I don't know what happens here. It looks like we've got 0 to increase. Technically, that's not a change from positive to negative. It's got to be a change from positive to negative to signal a relative extrema. So this looks like two places, and the only thing where you might have trouble is figuring out that first time interval. Now, the fact of the matter is that we don't know that that relative maximum happens at t equals 10. Maybe it happens somewhere between 5 and 10. And if it can happen somewhere between 5 and 10, it could also happen somewhere between 10 and 15. So really, that relative increase, or that place with a horizontal tangent line, could happen somewhere between t equals 5 and t equals 15. Also, since we have a 0 change here, we don't know where the actual 0 occurs. It doesn't necessarily have to happen at 27.5, which would be halfway in between 25 and 30. It just has to happen somewhere between 25 and 30. So first, answer the question. Two instances where we are assured of an acceleration being 0. From t equals 5 to t equals 15, the velocity increases and then decreases. So there must be at equals 0, acceleration equals 0, for a t between 5 and 15. And then as I'm thinking about the second 0, we know that between 25 and 30, the velocity is 0. So if you remember what that meant by Rolle's theorem, that means that actually the velocity is not equal to 0. The change in velocity is 0. So by Rolle's theorem, which we used in calculus A to justify relative minimum and relative maximum, by Rolle's theorem, there must be a place where A, which happens to be the derivative of velocity, is going to equal 0 somewhere in that interval from 25 to 30. So that's it, everyone. That's all of our chart problems, and I will see you next time. All right? Signing off.